In this class, we will discuss about the different types of sections, cross sections that can be used in steel beam design. So, classification of cross sections. So, of course, this I have explained in the first lecture also. You can refer that also with the graph. Now, for understanding this concept, let us take a symmetrical I section, which is normally used for design beams. So, these are the notations. So, you can refer table 2 of IS 800, which is there in page 18 for this classification of cross sections, as well as you can refer 19, page number 19 for this sketch. Different types of sections are given in page number 19, which are used for beams. So this is symmetrical I section where the neutral axis lies here, and that neutral axis itself is your Z axis, which is the major axis, and Y axis is the minor axis. BF is the width of line, TF is the thickness of line, the average thickness we have to take. R1 is called as the radius and root. So all these details for a particular given section, ISMB or ISLB or ISFB sections, it is available in the steel tables. You can refer the steel tables for that, for these values. D is the depth of the web, H is the overall depth. So here we are going to take half of the width of the flange, that is B. B is BF by 2, and the depth of web D is equal to H minus 2 times TF plus R1. 2 times because one is on this side, another one on this side. So these are the things we should remember to just have an idea of whether the given section or the assumed section in the problem is plastic or compact or semi-compact or slender. So these are the 4 types of sections we use in steel beam design. This I had explained in the earlier lecture also, lecture number 1, you can refer. So just I will take an example for row of rolled sections. We have for welded sections also, we have for channel sections, we have for L section, we have, and built up sections we have. So I will consider a rolled section. In the case of a rolled section, we have to decide whether the flange is plastic or compact, or web is also plastic or compact, because normally a beam section in steel design should be either plastic or compact to take care of the shear and the moment acting on the beam. So in the case of flanges, the classification runs like this: the ratio B by TF. So B is the half of the flange divided by TF, the thickness of flange. If this is less than 9.4 times epsilon, then the section is taken as a plastic section or class 1 section, where epsilon is root of 250 by Fy. Fy is the yield stress or the yield strength of that steel. Normally Fy will be 250, so then this epsilon will be equal to 1. If you substitute Fy as 250, epsilon is root of 1, which is 1. If it is other than 250, then the epsilon value will be different than 1. So if this value is less than 9.4 times epsilon, it is the very strongest section, that is the plastic section, where the entire strength of the material is utilized. In the second, suppose if the value lies between 9.4 epsilon to 10.5 epsilon, then we say the section is compact section, class 2, which is slightly lesser stronger than this plastic. And if the value lies between 10.5 epsilon to 15.7 epsilon, the section is semi-compact, and if the value is greater than 15.7 epsilon, it is taken as slender. So in the case of beam design, these 2 types of sections are normally avoided. Either it should be plastic or compact. These values, this range of values are given in this page, table 2 of page 18 of IS 800. So you please refer that. So similarly for the web portion, we have to check both flange and web portions for the type of cross section. For the web portion, so since I have taken a symmetrical I section, neutral axis at the mid lies at the mid depth, then we have to take this ratio D by TW. So as already told, D is the depth of the web, TW is thickness of it. So this ratio we have to take. If this ratio is less than 84 epsilon, then the section is plastic. If it lies between 84 epsilon to 105 epsilon, it is compact. If it lies between 105 epsilon to 126 epsilon, it is semi-compact. And if it is greater than 126 epsilon, it is slender. That means all the steel sections, it is not like RCC sections. RC sections are normally rectangular or T sections or L sections like that, whereas steel sections are majorly I sections, they are slender sections. So compared to the length, so your web thickness, flange thickness, they are all very small. So these are the range of values for checking for the web. So for other types of sections, you can refer those to pages 18-19 of IS 800. Table is there, sketches are there. You can refer that. Now let us understand this by taking an example of IS 200 at 194.2 Newton per meter. Normally, steel sections are designated with their weights per meter length weights. So 1 meter of this section weighs 194.2 Newtons. So for this section, ISLB 200 section, from these field tables, you can get these details. H value is more under, which is nothing but 200 mm. BF is 100 mm. TF is 7.3 mm. PW is 5.4 mm. R1. So all those things I have shown here. So these values are obtained from the steel tables. D is the depth of it, you have to calculate H minus 2 times TF plus R1, which comes out to be 166.4 millimeter. And epsilon, if you take Fy as 250 MPa, epsilon will be 1. Now we have to check whether the section is plastic or compact or semi-compact like that. So if we check, let us calculate D value. D is Bf by 2, which is 100 by 2, 50 mm. And D by Tf value we have to calculate for checking for flange. So this B by 2 becomes 50 by 7.3, which comes out to be 6.849, which is definitely less than 9.4 epsilon. Therefore, the section is plastic. Flange is plastic. Similarly, D by TW for the web, that ratio 166.4 D value you have to calculate, divided by TW is 5.4. If you take the ratio 30.81, that is less than 84 epsilon. So you can observe here, therefore it is also plastic. That means both flange and web portions are plastic sections here. So it is good for the beams, which we are going to consider. Of course, it depends on so many factors. So the section will depend on the type of load, boundary conditions, all those things. Suppose in case if you get one that is flange as plastic, web as compact, then you have to consider as for the lowest. That is, if either flange or web is compact, then section is taken as compact only. That means one may be plastic, another may be compact. Then you have to treat the section as compact section only. So this is how we can classify the different types of cross sections in steel beam design. So just I have given an example of symmetrical I section, and we have proved that this section has comes out to be plastic section. Similarly, you can try for ISHB 200, ISHB 200 like that. For different I sections, you can check whether it comes plastic or compact. And on the same lines, you can check for channel sections also, L sections also, built-up sections also. So when I later on, when I take up the design example, I will discuss some more properties of this.